In this video, I will discuss available energy. Here I will talk about the relationship between the fact that heat energy naturally flows from a place with higher temperature towards a place with lower temperature, and how this can be used to do useful work. I will introduce the concept of a heat engine and also the concept of a refrigerator. I will also discuss the efficiency with which heat is being transferred by those two types of devices. Let's first talk about available energy and define what that means. Mechanical energy can be completely converted into the internal energy of an object, and that was demonstrated by James Joule in his experiment, which I discussed in the previous lecture. In the experiment, he used a vessel filled with water and a system of paddles attached to a shaft. The shaft was connected to a mass via string, and so when the mass fell to the ground, the shaft and paddle started to turn inside the water, which then resulted in an increase of the temperature of water. The conclusion that Joule made was that the mechanical work done on the mass as it was falling to the ground was converted into internal energy of the water. Now, if the experiment were set up to start with hot water and the mass at ground level, we would never observe that the paddles would begin to rotate and the mass would rise up. The thermal energy stored in the hot water is just not available to use and do work. However, part of the internal energy can be used by implementing proper means to do mechanical work. So, available energy is the portion of the internal energy of an object or a system or a working substance that can be converted into mechanical work. We know that heat flows naturally from higher temperature region to a lower temperature region. For example, a hot cup of tea left on the table will cool off over time due to the thermal energy loss to the cooler surroundings. However, none of this thermal energy was used to do any mechanical work. To be able to utilize some of the thermal energy a hot object could provide, we need a device capable of converting that energy into mechanical energy and doing work as a result. Such a device is called a heat engine. A heat engine utilizes some of the internal energy, which we will call from now on thermal energy, of a hot object and converts it to mechanical work. So the heat engine takes part of the internal energy of the hot object, and this part we are going to call thermal energy, and converts that thermal energy into mechanical work. The most common example of a heat engine will be a car engine. A car engine, or more generally an internal combustion engine, is an engine that's an example of a heat engine. The working substance that provides the thermal energy for this engine to convert to mechanical work is the burning mixture of fuel and air in the cylinders of that engine. The heat that is generated during burning that mixture causes expansion of these burning gases, which then physically moves the pistons of the engine, which mechanically move parts in the drivetrain of the vehicle, and as a result the vehicle is moving. So the thermal energy generated by burning the fuel is converted into mechanical work that moves the vehicle. A very simple example of a heat engine was a Hero's engine. So this is of course a model of it. So we have a vessel that is filled with water, which has two arms that have openings in opposing directions. When the water inside here is heated to a high temperature, it starts to boil, steam is formed, and then if the top of the vessel is closed off, so steam cannot escape here. The only ways for the steam to exit the vessel is through the two arms. So we have steam coming out in that direction and then steam coming out in that direction, which causes this device to rotate like so. So the heat source is the hot steam inside the vessel, and the device is the heat engine that converts this heat to mechanical work, which in this case is rotation. Let's now look at the schematic of operation of a heat engine, or the principal operation of a heat engine. First, I will introduce some new terminology that will help us describe how a heat engine operates. We already know that naturally heat flows from an object at higher temperature towards an object at lower temperature when the two are in contact, or in general, heat flows from a hotter region of space towards a colder region in space. So I'm going to introduce the hotter region of space, and I'm going to name it hot region, and the colder region of space, of course, cold region. So now we know that heat flows from the hot region towards the cold region, so I'm going to indicate that direction of flow with an arrow like so. And of course, the width of this strip here will correspond to the amount of heat that flows from the hot region towards the cold region. Now, I can use part of the heat that's coming from the hot region to the cold region to do mechanical work by introducing a heat engine in between the two regions. And this heat engine is going to utilize the available energy from this energy flowing between the hot and the cold region to do mechanical work. So here is my hot region. Here is the cold region. And the heat engine I will place in between. And so we have heat coming in from the hot region. Portion of it is used by the heat engine to do mechanical work. And then what's left, which is less than the heat that's coming in from the hot region, is exhausted into the cold region. So this flow of heat here, and the amount of work, if they're done to scale, you would find out that the sum of the width of this strip and the width of this strip should be equal to the width of this strip. So the amount of heat that's coming in from the hot region into the heat engine should be equal to the amount of work done by the heat engine plus the amount of heat that is exhausted into the cold region. And this is a basic conservation of energy principle. Energy cannot be created or destroyed. Therefore, the amount of energy coming in should be equal to the amount of energy coming out plus the work done. In the context of a internal combustion engine, as I explained on the previous slide, the hot region is the cylinders of the engine where the fuel air mixture is burning, heat is generated, and then the heat engine itself, which is the car engine, has moving parts which will move other parts in the drivetrain, which will cause the vehicle to move. So mechanical work is generated. And then not all of the heat generated in the cylinders is utilized to do mechanical work. So some of that is exhausted into the surroundings. So the cold region in this case will be the surroundings of the vehicle. And the heat that's exhausted in the cold region will be the exhaust emissions from the exhaust of the vehicle, as well as heat generated from the operation of the engine itself. So the engine block radiates heat into the surroundings directly. In the previous lecture, I talked about the zeroth, the first and the third laws of thermodynamics. The second law of thermodynamics is related to the operation of a heat engine. The statement of the second law then is that it is impossible to build a heat engine to perform mechanical work that does not exhaust heat to the surroundings. In other words, you can never have a heat engine that can take all of the heat that is coming from the hot region and it converts it entirely into mechanical work. And there is, if nothing else, one simple reason, and that is that any heat engine will have mechanical parts that are moving with respect to each other. That means that there is friction generated inside the engine. And so when this friction is generated, the engine will release heat. There is another point to be made. The heat that is absorbed by the engine will eventually warm up or heat up the engine to the temperature of the hot region, at which point heat will start to leak out from the engine. Even if it's insulated as best as possible from the surroundings, it's very hard to stop all leakage of heat from the engine. So those two mechanisms will ensure that the engine can never convert all of the heat that is coming from the hot region to mechanical work. There will be always exhaust or heat exhausted into the cold region. Another way to state the second law of thermodynamics is that it is impossible to have a heat engine that can work between two regions of space that are at the same temperature. So again, the equivalent statement to the second law is that no heat engine can operate between regions at the same temperature. The statement of the second law directly says that there is no perpetual motion engines that can be created. They can never exist. Perpetual motion engines or machines can't exist. And the reason for that is very simple. Friction. Since in any mechanical device there are parts that move and friction is generated, energy will always be lost during the operation of the device. The idea of perpetual motion engine or machine is that some initial amount of energy is introduced to the device, engine or machine, and then that engine will start to operate. And after that, no longer energy is introduced from outside. The engine produces the amount of energy necessary for its own operation. However, because of friction, there will be always loss of energy to the surroundings, so eventually the engine will not be able to operate because it will have not enough energy to do so. And so perpetual motion engines or machines can't exist, and this is because of the nature of the second law of thermodynamics. The heat that is coming from the hot region is converted to mechanical work, and then some of that heat is exhausted into the surroundings. So not all of the heat is converted to mechanical work 100%. How can we judge how well a heat engine converts the heat that is coming from the hot region to mechanical work? This can be gauged by the efficiency of operation of the heat engine. The operation of the heat engine obeys the law of conservation of energy, as I stated before. Here is our hot region. Here is the cold region. And here is the heat engine. Let's abbreviate it with HE. So the heat that is coming from the hot region, I'm going to label with Q sub H. Then the amount of work done by the amount of heat converted to work by the heat engine, we will call W. And then finally, the amount of heat exhausted into the cold region, let's call Q sub C. So then the conservation of energy equation becomes QH is equal to QC plus W. The heat supplied by the hot region is equal to the work done by the heat engine plus the heat released into the cold region. So then the efficiency of the heat engine is labeled with the Greek letter eta, and it's calculated as the work produced by the heat engine divided by the heat that is coming from the hot region. And this is usually expressed in percent. So in order to do that, you would multiply this by 100 to get it in percent. Typically, for modern heat engines, the efficiency is between 20 and 25%. The human body, if looked at as a heat engine, has an efficiency of about 20%. Let's look at the following example involving the efficiency of a heat engine. An engine operates with an efficiency of 20%. If the engine has a power output of 15 kilowatts, how many joules does the engine exhaust in the cold region? From the lecture about work and energy, remember that power was defined as work divided by time. So P, power, is equal to the work W divided by time T. That will be equal to 15 kilowatts, or that is 15,000 watts. So from here, I can calculate that in 1 second of time, the work output will be equal to the power times the time, so that will be 15,000 watts times 1 second, but this is 15,000 joules. Now let's look at the efficiency. The efficiency eta is 20%, which expressed as a decimal is 0.2, and this will be equal to the work done divided by the heat coming from the hot reservoir. So then from here, the amount of heat that is coming from the hot reservoir will be equal to the work done divided by 0.2, and this is 15,000 joules divided by 0.2, which is equal to 75,000 joules. So this is the amount of heat that enters the heat engine from the hot region. Now, since we are looking for the amount of heat exhausted in the cold region, I can use the equation of conservation of energy, or the principle of conservation of energy, and the equation that I stated on the previous slide. And that was that QH is equal to W plus QC. So from here, QC will be equal to QH minus W. So that is 75,000 joules minus 15,000 joules. And that is equal to 60,000 joules. In one of the previous slides, I stated that, and that is the statement of the second law of thermodynamics, of course, that the heat engine can never convert the heat coming from the hot region entirely into mechanical work. There will always be heat exhausted into the cold region. I discussed two predominant methods why heat exhausted to the cold region. One was heat generated by the operation of the engine by burning the fuel inside, and the other one was heat generated by friction between the parts of the engine. If there was a way to produce an engine that does not experience any friction between its parts, then the efficiency with which that engine will convert heat coming from the hot region to mechanical work will increase. It will be bigger than the efficiency that I discussed in the previous section. So, this type of engine, which does not have internal friction, is a theoretical model of an engine, or an ideal engine. This type of engine cannot exist in reality, but if it was possible to produce an engine without internal friction, this engine, as I said, will be called ideal or theoretical engine. And this engine will have higher efficiency than the efficiency defined in the previous slides. This new efficiency, the efficiency of the theoretical or ideal engine, is called theoretical or ideal efficiency. Ideal or theoretical engine is a heat engine which has no friction between its parts, and the efficiency of such engine is called theoretical or ideal efficiency or Carnot efficiency, after the French physicist or engineer who came up with the idea of this ideal engine. Before I define theoretical or ideal or Carnot efficiency, let's look at again the hot and cold reservoirs. Here is our hot reservoir or region. Here is the cold region. The amount of heat that is coming from the hot region will be converted partially to work, and then what's left will be exhausted into the cold region. Okay, but the hot region is characterized with a certain temperature, which I'm going to call TH. So this is the temperature of the hot region. Then the cold region is also characterized with a certain temperature, and that will be the temperature of the cold region, TC. And then the ideal heat engine is placed in between the two regions. And so again, heat comes in from the hot region, it converts into work, and then some, or what's left, is exhausted into the cold region. So then the theoretical or ideal or Carnot efficiency, eta C, is defined as 1 minus the ratio of the temperature of the cold region to the temperature of the hot region. This is calculated by converting the two temperatures in Kelvin. So Tc and Th must be in Kelvin. If you keep those in Celsius, you are not going to get the correct answer or value of the theoretical efficiency. Just as a reminder, the conversion between Celsius and Kelvin is done with the following relationship. The temperature in Kelvin is equal to the temperature in Celsius plus 273. Here is an example problem that is using the definition of theoretical efficiency, and the problem reads: a heat engine takes 1000 joules of energy at 727 degrees Celsius and exhausts 600 joules at 227 degrees Celsius. What is the theoretical efficiency of the engine? So looking at the two temperatures, we can tell that the temperature of the hot region, TH, is equal to 727 degrees Celsius, which we need to convert to Kelvin. So this will be TH is equal to 1000 Kelvin. And then the temperature of the cold region, TC, is equal to 227 degrees Celsius, which is equal to 500 Kelvin. The theoretical efficiency is equal to 1 minus Tc divided by Th, so that is equal to 1 minus 500 Kelvin divided by 1000 Kelvin. This is equal to 0.5, or this is 50%. If I did not convert the temperatures to Kelvin, then the calculated theoretical efficiency would have been 1 minus 227 degrees Celsius divided by 727 degrees Celsius, which gives 0.69 or 69%. So as I stated before, when calculating the theoretical efficiency, the two temperatures must always be converted into Kelvin. You cannot leave them in Celsius.